Good morning, all of you. My name is Kiran Kumar. Subject is physics, and I am teaching for +1 students. And the topic today we are teaching is in oscillation chapter a simple topic, that is simple pendulum. So we'll discuss about what is a simple pendulum and the expression for time period of the simple pendulum, and we'll see some of the applications of simple pendulum. Simple pendulum. So, what is the definition of simple pendulum? Here, a simple pendulum is nothing but a point mass suspended by a inextensible massless string or thread, that is considered as a simple pendulum. So, in the nature, we cannot have the point mass and inextensible and negligible mass string. So that is an ideal simple pendulum. So practical purpose of simple pendulum, that is in practice, simple pendulum is considered as a heavy small metal bob, that is nothing but a metal sphere is suspended by a inextensible and torsionless massless string, negligible mass will be present, but it is a negligible mass, that is considered as a simple pendulum for practical purpose. So we'll see the diagram of the simple pendulum. Here, this is a simple pendulum diagram. And this is a metal bob, and this point is called as S, and it is point of suspension. And this is the point of rotation. And the distance between this point of rotation to the point of suspension, this is considered as the length of the pendulum. L is the length of the pendulum. Now here, suspension to the center of the bob. Whenever we are measuring, we will in practical, the length of the pendulums is constant. That is, we will take the length is 50 centimeters. But whenever we want to measure the L, the exact point, that is the center of the bob, where the total mass is considered, that is exactly we cannot determine. That's why we'll measure the radius, that is this is the radius of the bob, and we will include, that is from point of suspension to the bottom of the bob, the total is taken as A is from point of suspension to bottom. Therefore, automatically L becomes the, what is the length, that is A minus R. R is the radius. In that way, we will, whenever we want to put the length, for example, the radius I got is 1 centimeter. So A I will consider as the L minus A is equals to 51 centimeters. L automatically becomes 50 centimeters. So length of the pendulum is nothing but from point of suspension to the center of the bob, that is where the gravity or mass both are concentrated. We know for small bodies the mass, total mass, that is center of mass and center of gravity will coincide. So this is called as length of pendulum. Now we will see the time period for the pendulum, that is expression for time period of the simple pendulum. So the expression for time period t is equals to 2 pi under root of L by G. This is the expression for the time period of the pendulum, where L is length of pendulum. L is called length of pendulum, and T is time period of pendulum, and G is acceleration due to gravity. So this is the expression for time period of the simple pendulum. By this we can determine the acceleration due to gravity at a place. That is, this equation is squaring on both sides. T square is equals to, we will get 4 pi square L by G square. L by G. This is the squaring on both sides. Then G is equals to 4 pi square L by T square. This is the determination of acceleration due to gravity formula. L is the length of the pendulum and T is the time period of the pendulum. So, practical purpose, the determination of G formula is this one, and we will discuss the expression for time period of the simple pendulum. Here, this is the equilibrium position. So we are once again coming into the diagram. This is the metal bob at equilibrium position O, and now we are pulling the pendulum slightly to a side, making small angular displacement theta. Then at this position, at equilibrium position, the weight will act vertically downwards and the tension in the string will act vertically upwards. So at this position, let us suppose we are pulling slightly to a side, and at that it is released, the pendulum will oscillate, that is to and fro motion. Here the displace, that is making angle, is very small. So for small angular displacements only, the pendulum will be in SHM. So for small angle, whenever it is at P and it is released, it will oscillate about this mean position O. At position P, the forces acting is, weight will act vertically downwards and the tension in the string vertically upwards. Let us consider this is T1 and this is T2, and the mg is resolved into two components. One is mg cos theta and another one is mg sin theta. This is the mg sin theta and this is mg cos theta. This angle is theta. Now this is the displacement of the pendulum from mean position to this point, that is considered as x. X is the displacement and theta is the angle made with the vertical at the point of suspension. Now we will see the expression for the time period of the simple pendulum. So here this is the diagram whenever it is at position P. Initially at equilibrium, position, the tension T1 is balanced by the weight mg, and at p the mg is resolved into two components. One is mg cos theta and another one is mg sin theta. So this mg cos theta, that is balanced by T2 is equals to tension in the string, that is tension is balanced by mg cos theta, and the unbalanced component, that is mg sin theta, this is equals to the restoring force. So the unbalanced force is equals to F is equals to mg sin theta, and it is minus. The negative sign indicates that it is a restoring force, that is only it always tries to restore. Restore means restoring, always tries to bring the pendulum towards mean position. So this negative sign indicates that the mg sin theta is a restoring force. So now we know that if a is the acceleration, then F is equals to ma, and if you substitute that one, ma is equals to, that is minus mg sin theta. This is the m and m will cancel, a is equals to minus g sin theta. That is the, if theta here, this is the one equation, theta is very small, theta is very small angular display, it makes a small angle, then we can take a sin theta is approximately equals to theta. This sin theta is approximately theta, and a is equals to, we are getting as minus g theta. This is the second equation. Before initially, let us consider this is a total sphere, and this is the center of the sphere, and L becomes the radius of the sphere. Now we know that angle is equals to angle theta is equals to length of arc by radius, length of arc by radius. Therefore theta is equals to x by L. This x is called as some portion of the sphere, that is length of arc, then theta is equals to x by L. This is first equation, and this is the second equation. So substitute this theta value here, then a is equals to minus g into x by L. This is the equals to minus g by L into x. So g is a constant, and L is also constant. Therefore we can write this a is equals to minus gx. This equation becomes a is equals to minus g by L. Once again I am writing that equation, minus g by L into x. Both these two are constants, therefore I can write acceleration is directly proportional to displacement and opposite in direction. So this is the third equation. This is the second equation. Here now the pendulum is in SHM. The pendulum is in SHM. That is, it is satisfying the conditions of SHM. One is it is a periodic motion, first one. Second one is it is a to and fro motion about this mean position, and third one is the acceleration is at any point, the acceleration is directly proportional to displacement and opposite in direction. and the fourth one is the acceleration is towards mean position. It is acting towards a mean position. Therefore, the pendulum is in SHM. So, if it is in SHM, we know that at any point the acceleration is equals to, we can write as minus omega square x. A is equals to minus omega square x. Let us consider this is the third equation and this is the fourth equation. Now comparing 3 and 4, we will get comparing third and 4. What we will get is, we will get that as 3 and 4, we will take this is 3 and this is 4. Here A is A and x is x, omega square is equals to G by L. Then omega is equals to under root of G by L. Then we know that T is the time period. So time period is equals to 2 pi by omega, that is 2 pi by omega is under root of G by L. It comes to numerator, T is equals to 2 pi under root of L by G. This is the an expression for time period of the simple pendulum. Here we are taking the acceleration is towards mean position and acceleration is directly proportional to displacement and opposite in direction. Therefore, from this equation, from here, we are considering that the pendulum is in SHM. If it is in SHM, at any point the acceleration is given by this formula, or we can do this in another way, that is from here onwards, that is acceleration is directly proportional to displacement and opposite in direction. Therefore, I can write this as a acceleration directly proportional. From that, I can write time period is 2 pi under root of displacement by acceleration. Displacement by acceleration. So, here from 3, A is equals to minus G by L into X. X is the displacement, A is the acceleration. So, we know that displacement by acceleration, that from this I can write x by A is equals to L by G. This negative sign only indicates that that is in acceleration is towards mean position. Therefore, x by A is L by G is substituted here. Then I will get time period T is equals to 2 pi under root of L by G. This is the another method of doing the expression for the time period of a simple pendulum. So here in this we will discuss the laws of simple pendulum. T is equals to 2 pi under root of L by G. This is the expression for time period. From this we can write the laws of simple pendulum. That is, T is directly proportional to root L, that is the first law, and T is inversely proportional to root G, that is acceleration due to gravity, and T time period does not depends on mass of the bob. That is, if you replace the bob which is made with wood and another bob, it is wood bob is replaced with the metal bob, the time period does not changes. Therefore, these are the laws of the simple pendulum. One is time period is directly proportional to the L, length of the pendulum. Time period is inversely proportional to the root G, gravity. That is, gravity is more, the time period is less. Length is more, time period is also more. So directly proportional, and time period does not depend on mass. These are called as the laws. And also, if you take the applications of the simple pendulum, if the simple pendulum is in a lift hanging from a roof, then the cases, that is, this is a lift and a pendulum is hanging here, the weight will act vertically downwards and tension is upwards. First, it is at rest, the lift is at rest or moving with uniform velocity, then the time period equation is 2 pi under root of L by G. This is time period if the lift is moving with uniform velocity or it is at rest. In the same second case, that is, if lift is moving upwards with an acceleration a, then time period becomes 2 pi under root of L by G plus a. If third one, the lift is moving downwards with an acceleration a, then time period is equals to 2 pi under root of L by G minus a. If the lift is freely falling, that is, the wire is broken, then a is equals to G and we'll get time period is equals to 0 or frequency is equals to infinity. So these are the some cases if pendulum is in a lift hanging from a roof of the lift. This is the lift and it is hanging from the roof. Then if it is at rest or moving with uniform velocity, the time period does not changes, L by G. If it is moving with uniform acceleration upwards, then time period is L by G plus A. Here, lift is moving downwards with an acceleration, time period is 2 pi under root of L by G minus A. If lift is freely falling, then time period is equals to 0. So these are the some special cases if the pendulum is suspended from the roof of a lift. Here, if you observe, the pendulum is taken from the ground to certain height, a clock pendulum, clock pendulum. So it is taken from the mountain. This is a mountain, and the pendulum clock is taken from bottom to the top of the mountain. What happens to the time? It gains or loses the time. Here we know time period is inversely proportional to gravity. We all of you know that the gravity will decreases when we are going to height. Height increases, gravity will decreases. Therefore, gravity is decreasing and time period will increases. Time period is increasing is nothing but the time taken. What is time period? The time taken to complete one oscillation is called as time period. So whenever it is taken, the pendulum clock is taken from the bottom to the top of the mountain, then we'll observe that the gravity will decreases due to height increases, gravity will decreases. Gravity decreases means time period will increases. Time period is increasing, nothing but number of oscillations decreases. number of oscillations will decreases. Therefore, the per day the oscillations will decreases. Therefore, the time will gets lost. The time of pendulum gets losses. This is the one of the applications of the simple pendulum. How the time period depends on gravity. So that is the small topic expression for time period of the simple pendulum. And this we are having the in this LT square graph, that is L is taken as on x-axis, time period is taken on y-axis. The LT square graph is a straight line passing through origin. Here the seconds pendulum. What is a seconds pendulum? Seconds pendulum is nothing but the pendulum whose time period is t is equals to 2 seconds. That is called as a seconds pendulum. So a pendulum whose time period is 2 seconds is called as seconds pendulum. If t is equals to 2 seconds, then t square is equals to 4. And from the equation t square is equals to, we know that 4 pi square. We know time period equation is t is equals to 2 pi under root of L by G, and squaring on both sides, t square is equals to 4 pi square L by G. If t is 2 seconds and t square is 4, therefore it becomes 4 is equals to 4 pi square L by G. That is, the 4 and 4 will cancel. Length of the pendulum is given as length of seconds pendulum. We can take L is time is 2 seconds. Length of seconds pendulum is given as G by pi square. This is the length of the seconds pendulum. So if G is approximately taken as 10 and pi square is approximately taken as 10, L is equals to 10 by 10, that is equals to 1 meter or 100 centimeters. This is the length of the pendulum on earth, seconds pendulum, length of seconds pendulum on earth, that is about 1 meter or 100 centimeter. From this graph also we have to show that length of the seconds pendulum is 100. That is, by drawing the graph, the time is 2 seconds, seconds pendulum. This is 4, and if you draw a line that touches the graph at one point, from that perpendicularly on x-axis, if you draw a line that should touch the line on x-axis at 100 centimeters. So that is the small topic we are completed. How what is a simple pendulum, and how we have to derive the expression for the time period of the simple pendulum. The time period of the simple pendulum is 2 pi under root of L by G, and some applications of the simple pendulum. Thank you.